All right, so we're going to give this a try. It's the first time I've done a recorded lecture without having a class in the room with me. So we'll keep this relatively short. So just a recap, we ended talking about precipitation reactions last Thursday. And a reminder that precipitation reactions are really just when you make a combination of ions that won't stay dissolved. They stick to each other too well to stay dissolved in a liquid, and so they fall out of the liquid, and that's what we call a precipitation reaction. So as we mentioned last week, there's tons of different versions of solubility tables, solubility charts, and all of them are just approximations. Every single one of these solubility rules is just, the general rules. The main reason that we have them is because we don't actually want to go look up a solubility value every time, because technically everything is slightly soluble in water. When we say something's insoluble, we mean that its saturation point might be 1 × 10⁻⁶ moles per liter. So, but it's still a little bit of it still dissolved. So I just want you to understand that all of these solubility tables and solubility charts are approximations. We can get more specific and get better numbers if we're really willing to run the math for all of these situations. So don't get too hung up on which version of the solubility charts you're using or solubility tables you're using, because what matters most is that you know how to use whatever you're given. So I'm personally pretty fond of this version of the solubility rules, which I just grabbed straight from Wikipedia. If you look at Wikipedia's article on solubility, I don't remember if it's solubility rules or solubility chart, but basically they have a open source, really simple, easy to read, in my opinion, list of solubility rules. And that covers pretty much most of the common ions that we're going to deal with in this class. So just for starters, if we wanted to look at these example problems, the way we would do this is we look at it at what we start with. And this is where that term double displacement reaction comes in, because really what we're going to do is we're just going to swap the two sets of ions to see if we make a new combination that doesn't dissolve anymore. So sodium nitrate tells us it's aqueous to start with, and then if we go down here, we can say, okay, well, group 1, that's sodium, and it's soluble except lithium phosphate. So we know that sodium ions are going to be soluble. And we also know nitrates is on our list of mostly soluble, with no exception. So all nitrates are soluble, which makes sense. So this combination should be soluble because it's already dissolved. Potassium chloride, well, potassium's also in group 1. So we know the potassium doesn't have any, is going to stay soluble and doesn't have any exceptions. And then chloride, just to double check, chlorides are soluble except for silver chloride, lead 2 chloride, copper 1 chloride, and mercury 1 chloride. So since we don't have any of those exceptions here, when we switch this combination to go, okay, well, if sodium nitrate is soluble, let's try potassium nitrate, see if that's soluble. And we come down here and we say, yeah, potassium nitrate is also going to be soluble. So it's still aqueous. And our other possible combination is sodium chloride, which we know from everyday life is soluble as well, but also matches up down here. Group 1 is soluble, no exceptions. So if we were writing this out, we didn't make any new combination that comes out of the solution. So even though I wrote our two possible combinations, the fact that they both stay aqueous means we're actually going to write no reaction. Because we started We started with sodium ions and nitrate ions and potassium ions and chloride ions all floating around dissolved in water. And when we mix the two solutions together, we still have all four of those ions floating around. So nothing changed. We do sodium chloride and mercury 1 acetate. Well, mercury 1, so we know chlorides are usually soluble. We know that sodiums are always soluble, no exceptions. And we know, we come down here, acetate is also always soluble, with the exception of silver acetate, which is still soluble, it's just less soluble, going back to what I was saying earlier. These are all approximations, but we don't have any silver involved here, so we don't need to worry about that right now. So chlorides are soluble except for silver, lead 2, copper 1, and mercury 1. We do have mercury 1, so we know that we're going to make mercury 1 chloride. And mercury 1 is just sort of a weird exception where when mercury 1 exists, it exists as what's called a dimer. Means even though each mercury has a charge of +1, they stick together in this weird sort of combination. So even though it's Hg2 with a 2+, it's still mercury 1 if we're just looking at the charge. And so going back to make a solid product, mercury 1 is one of our exceptions for chlorides. Chlorides are soluble except for these 4 exceptions. So that means we're going to write it as solid. And then our other possible combination is sodium ions and acetate ions. Those are still going to be floating around because sodiums are soluble, no exceptions. So NaC2H3O2 aqueous. And now we can actually look at balancing if we wanted to, because we need 2 chlorides here, and we started with 2 acetates. Excuse me. So our final answer would look like that. And we would, in fact, have a solid product. All right. Moving things along. Ammonium sulfate. Ammonium is soluble, no exceptions. So we know that our ammonium is not going to be part of our solid product. Sulfates we haven't dealt with yet. So sulfates, we come down here, we find them on our table. They're under their soluble category. They're soluble except for those exceptions right there. Silver, lead 2, barium 2, strontium, not barium 2, barium's always a +2, strontium ions and calcium ions. So we've got sulfates and we've got strontium. That tells us right there we're going to make a solid product. Strontium sulfate is going to be a solid. And our other possible combination is the ammonium and chloride. Ammonium chloride is going to stay aqueous. And again, we would want to balance it for our final answer. Last example, ammonium chloride. We know ammonium is going to be soluble, no exceptions. Chlorides are usually soluble, but silver ions are one of our exceptions. Silver ions are pretty insoluble with almost everything. So silver ions, if you see silver, there's a good chance that's going to be part of your product. So silver chloride is going to be a solid, and then our other combination is ammonium nitrate. fun. These are actually both historically significant molecules. Silver chloride is really instrumental in the early forms of photography. They would use silver ions and chloride to make a solid adhere to a piece of paper that had been exposed to sun. So basically, the earliest forms of photography were a precipitation reaction. They've just very selectively precipitated where light had been exposed on a plate of glass that had been previously treated. And then on the other side, ammonium nitrate is the very first synthetic fertilizer was ammonium nitrate, and it actually has a really big history that is really influential in the way World War I played out. That if anybody's interested, ask me next time I'm on campus at STHS, and I can tell you the story of the Haber process. Fritz Haber invented the way of making ammonium nitrate in the lab, and it was really important during World War I. All right, so that's some practice with the precipitation reaction. The only new thing I'm going to add today is what's called the total ionic and the net ionic form of these reactions. So these reactions, the way that we just worked through them, what's called the molecular form. The ionic form basically splits up these starting materials and the products into the individual ions. Because remember, we don't actually have sodium nitrate molecules floating around when they're dissolved in water. We actually have sodium ions floating and nitrate ions floating, like that simulation that we talked about last week. So the total ionic form of the precipitation reaction is just write everything as separate ions unless it turns into a solid. Yeah. Sorry, getting my slides. This is just another example of one of those different types of solubility tables that I was talking about. In this case, it presents everything instead of just a list of rules. It presents it as a table. And then you can see that this one also has slightly soluble as well as insoluble and soluble. So this one's just a little bit more detailed, and you would just, the way you use this, be very similar to the way that you use the solubility rules, except in this case, you just find your specific ion. So here's sodium. We know sodium is soluble with everything. And when we look down this column, that's what it shows. So we wanted to see, for instance, if calcium carbonate is soluble. If calcium carbonate is soluble, we're going to find calcium right here. We're going to find carbonate right here. And where they intersect, you see insoluble. All right, so here's an example of the total ionic equation versus a molecular equation. So here, this is lead nitrate reacting with potassium iodide to make lead iodide as a solid, and potassium nitrate, which stays dissolved. If we split everything up into its individual atoms or ions, our total ionic equation just takes that lead 2 nitrate and turns into lead 2 ions, nitrate ions, and turns potassium iodide into potassium ions and iodide ions, all of them aqueous. And when we mix them together, we made one compound that's insoluble, lead 2 iodide, it's insoluble, so we write it in its molecular formula with solid written next to it. But then the potassium iodide, or so the potassium ions and the nitrate ions still stay dissolved. So we still write them as their separate ions, and we still write aqueous behind each of them because they're still in solution. So that's the total ionic equation. You just write everything as its individual ions, and then if you make a new solid, you write that in its molecular form. The net ionic equation basically says that anything that doesn't change, don't bother writing it. So for the same reaction we had above, the potassium ions and the iodide ions still stayed dissolved. They didn't really do anything. There's what we call spectator ions because they're just there watching as the ions had eyes. So they're called spectator ions. And what you do is with the net ionic equation, you just get rid of any spectator ions. Anything that doesn't change between reactants and products just cancels it out. You can treat these balanced reactions like they're algebra expressions. And if we had an algebra expression that had +2 on both sides, on the left side and the right side, you just subtract 2 from both sides and it would disappear, right? We can just subtract 2 potassium ions from the reactant side as long as we also do it to the product side. And what we get is the only things that we write in this case is what we actually turns into our solid. So we write the lead-2 ion plus the iodide ions form lead-2 iodide as a solid. So net ionic equations are actually the shortest or the easiest to write. All right, so I think that's enough for right now. I'm gonna stop the recording and post this, and you'll see this, and then I'll check in with everybody before the end of class today. Make sure that this all made sense and you were able to see the video and everything. All right, thanks. Have a good day.